such a mess. Why? Okay, so there's my function using the quotient rule. Look, I was about to write on my iPad with that. Using the quotient rule, f prime of x is going to be low d high, so low times the derivative of the top minus high d low, the top times the derivative of the bottom, all over low low, which means just this thing squared. All right, so that's the derivative. I know it's super confusing or looks confusing, but you'll get used to this after a while. I just gotta admit, when I first learned this, I avoided it at all costs, like the quotient rule. So if you don't like it and if you want to try to avoid it, that's fine. There's ways. In fact, I will tell you after Friday, I'll show you some tricks. I can't show them to you now because we don't have the equipment. There's a there's another rule that we can use in place of this, but for now we're stuck with this. Okay, so there it is. That's the quotient rule. So that means if I want to compute f prime of 1, that's going to be h of 1, g prime of 1, minus g of 1, h prime of 1, all over h of 1 quantity squared. All right, now I just need these numbers. So let's see, going back to the graph that we have here, you can find the numbers on the graph. Let's see, first of all, this is g. So g of 1, zoom out. Okay, g of 1 is 7. G prime of 1, it looks like this is a slope of negative 2. Is that right? Over 1 down 2. So rise over run would be negative 2. So g prime of 1 is negative 2. G of 1 is 7. I'm going to jot this down over here because I can't remember it all. G of 1 is 7. G prime of 1 is negative 2. And then h, let's see, h of 1, oh, come on. Why did they do this to me? Okay, h of 1, it looks like is about, it's 3.5. I'm going to go with 3.5. H of 1 is 3.5. And then the slope, come on, why couldn't they have done this a little bit nicer? What is that slope? Okay, it looks to me like it's going from here to here, over 1, up 1. I'm going to go with a slope of 1 and hope for the best here. Okay, so the slope here is going to be 1. That's what I'm going with. And if it doesn't like me, I'll complain to the management. Okay, so there it is. And now we just have to plug and chug. So the rest of this should be pretty easy. H of 1 is 3.5. G prime of 1, negative 2. G of 1, H prime of 1, all over H of 1 squared. How's that look? That looks okay. I don't want to do this. Oh, wait. I can do it in my head, most of it. This is going to be negative 7 minus 7, 3.5. That's going to be 10 point. Let me just do this on my calculator. That's a piece of junk. Just a sec. 3.5 squared. Oh, 12.25. How could I be so far off? That's weird. Interesting. 12.25. All right. So 14 over 12.25, negative. I wonder if it likes that. Let's check it out. I'm just going to do this for fun. Okay, so I experiment mainly so you don't have to. Negative 14 divided by 12.25. And we'll see if it likes it. Yeah, it liked it. Okay, so apparently you can type it in like that, even though that's kind of ugly, but it works. All right, there you go. You happy now? Okay, it's good. So yeah, I pushed the due date back half an hour. So if you're still working on it, you can type it in quickly and get it done. Yeah, I should probably do that every day, is have the due time be like 8:15. That way, if there's like one problem that you need to not enough time to do them all, but maybe I'll think of that for after break or after the first test. Yeah, I know. I think of it as a break because I don't have to plan anything for Friday because I've got the test already written up. All right, what else do we need to look at from this homework?
Problem 7.
7, right above this one. Very nice. Let's take a peek. Right there we go. Okay, so we need the derivative and then the second derivative. The second derivative is the one that's going to be a little bit harder. Let's go ahead and get the derivative though. Give me a sec here. So F, you might have something slightly different from this, but we're still going to use this quotient rule. Okay, so let's do I'll get both of my derivatives and then I'll go plug in the number. It kind of is annoying that this is little f of x, and I used little f of x in my definition for so I'm going to change colors. So 1 minus 2x, g of x is 1 plus 2x, f prime is negative 2, and g prime is 2. So far, that's hopefully, the setup. Now, I need to remember the quotient rule. The quotient rule is low d high, so g of x times the derivative of f of x minus f of x times the derivative of g of x all over g of x squared. By the way, you'll probably get this wrong at least once, maybe more than once. It's so easy to reverse these and do these backwards. So just be, cut yourself some slack when you get it wrong on the next quiz or on the test. It's okay. I mean, you're learning, and it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. It's just so easy to get those backwards. So anyway, getting back to this, let's go ahead and plug all this junk in. G of x was 1 plus 2x times f prime of x minus f of x, 1 minus 2x times g prime of x all over 1 plus 2x quantity squared. So this, I should have changed back to this pink color. That's the pink f, that one up there. It's down here. Let me simplify that because I'm going to have to do a second derivative. So I mentioned that if you don't have to do anything with this, then you just leave it. Leave it the way it is. No sense in simplifying it. It's too much work. So, but here I do want to do something else with this, so I'm going to have to do a little bit more work. So give me a sec here. Minus 2 plus 4x all over 1 plus 4x plus 4x squared. Okay, so just to explain, I distributed the negative 2 here. Got this. And I distributed both this 2 and this negative sign. So when you distribute the 2, you get 2 minus 4x, but then negate it, so it's negative 2 plus 4x. There it is. So there's f prime. So far, so good? I'm guessing that that wasn't the problem with this one. It was the second step. But, we need this to get the second step. The second step is the f double prime. So back to the drawing board. Let me pick a different color. How about blue? Okay, so in blue over here, I have f of x is the top function. G of x is the bottom function. F prime is 0. G prime is 4 plus 8x. So double check my math over there. That's really little. Let's see, can I make it a little bit bigger? Here, how's that? So all I did was I took this, that's the top, this, the bottom, and I'm just sort of on the side keeping track of my derivatives so that I know what I'm going to plug into the quotient rule. It's always good practice. I mean, I don't know. Here, let me show you. This is from Calc 2. Give me a sec. Give me a sec here. I know I saw some things. Okay, maybe this isn't a good. I remember maybe it was earlier. There was a quiz. So like this guy wrote down a ton of stuff. That was great. This other person, I don't see anyone. Didn't write down as much. Got the right answer, but some people that wrote down almost nothing got the wrong answer. And it's impossible, well, maybe not impossible, but it's hard for me to tell what they did wrong. So the more you write down, the more I'm able to help you to get it right the next time. So write down what you can over on the side, whatever, and then put it all together. Okay, so now we put it all together. F double prime, so second derivative, low d high, so that's the bottom. In this case, that's 1 plus 4x plus 4x squared times the derivative of the top minus the top times the derivative of the bottom. I'll zoom out in just a second, all over the bottom squared. There it is. Okay, so take a minute, make sure that that makes sense. Now, we don't have to do any more derivatives, so I'm not going to simplify that anymore, except to point out that 0 times this is 0. So I will point that out. So let me just put a little line through all of that so that I don't bother computing that when I get to my final answer. But there it is. There's my derivative, second derivative. Now the rest of this you know how to do. You're just going to plug in the number 3. Let's go ahead and do, or whatever number you have. So let's do that here. So where's my, change this to this color. So we got f prime of 3 is negative 4 over 1 plus 12 plus 36, which is negative 4 over 37, 47, 49. How's that? And then f double prime of 3 is going to be, let's see, 4. Maybe I can't do this one in my head. It's 24, 28. 28 times 4 is 112. Let's see if I can do my mental arithmetic correctly. And then on the bottom, 49 squared. I should know this. 49 squared. It's going to be 2,500 minus 2,501 minus 100? 2,000 or minus 50. So is it 2,451? Let's see if. Oh, okay. I had it right the first time and then I corrected it. So it's 2,500 plus 1 minus 100. Oh, yeah, because it's 50. Never mind. Yeah, 401. Thank you. I always like to challenge myself with my mental arithmetic. Let's see if I got both of these right. So here it is, negative 4. You would, of course, want to do it on your calculator to make sure you got it right. You don't have to challenge yourself to do it all in your head like I do. I only do this because I'm getting old and I want to make sure that my brain is still working. Okay, so there they are. And let's just hit enter and see what happens. I got them right. Good. Whew. Okay. So I wonder, would this do decimals? Just a minute. 4 over 49. Let me see if this likes decimals or if it wants you to have a fraction. 0. Where is it? 0.8162. Will it let me do another? Just submit this one again. Okay, apparently it doesn't mind it if you have a decimal as long as it's, oh, look at that. How many digits is that? It's ridiculous. But anyway, so apparently it doesn't mind the decimals. I kind of prefer the fractions. But yeah, I don't know how many digits does it, have you experimented? How many digits does it require? Okay, so if I go to this many, it'll say no. Let's see what happens. Ah, see, yes, you're right. So let's change this to, oh,
I think it might be 3 non-zero.
okay, well, whatever, yeah, so use 3 non-zero, I guess. I've exceeded the number of tries for this one because it won't let me change that one now, but that's okay. All right, well, I've goofed around enough. What other issues do we have, if any? So you got the quotient rule figured out, low D high minus high D low over low low. That one's the hard one. And then the product rule. There's 2 problems on your quiz. It's just do the derivative of a product, do the derivative of a quotient. That's it. So if you can get those in your head, you're going to be in good shape. Let me go ahead. We'll pass this around. Just practice. Remember, it's practice. It's helpful. Hopefully this will help you get an A on the test on Friday. So here you go. There you are. Enjoy. Here's one for you. Here's one for Stina. Special delivery back here. Very nice. Just to point out, when you do these, you don't have to simplify them. So don't feel like you have to expand anything. Just write your answers using the quotient rule and the product rule and leave it unsimplified. It'll be a lot easier for me and quicker for you. some of you are done. Don't hurry. Well, it shouldn't take you too long. Look at yours. Is this yours?
Oh, that was the test.
Okay, so I got yours already. Oh, what are you? No, don't simplify it. Don't do it. You put it off. That would be terrible. What's the worst? Yeah, expanding that. All right, you got the last one here. You can do it. Did you simplify? You did something. Yeah. Excellent. Oh, yeah, you were. Yeah. I'm not going to look below this line.
That's fine. I was already done with it by the time you said something.
All right, I'll show you mine, and this is just to see if you know the quotient rule and the product rule. It's not to make you do a lot of algebras. That's why I said don't expand or simplify in any way. So here's what I have. This is the first one. So and I labeled these because you might have done it in a different order, but I've mentioned that everything is commutative, which means you could switch the order and everything would be good. So I can't remember what I had in my notes, but I always just, as long as you have sort of this mixing up of the things like f times g prime, g times f prime, you could do f prime times g plus f times g prime. However it is, as long as you have those two components added together, you're good in any order you'd like. Here, I'll just do another version just so that you see. I could have done this, f prime times g x plus 7 plus f minus 3x plus 1 times g prime. So it's the same thing. So this is f prime times g plus f times g prime. Yeah. So a bunch of different ways you can jumble it up as long as you have those four things in some sort of a, the main thing is to have the f with the g prime and the g with the f prime, and then you're good. So the quotient rule is less forgiving, so you have to make sure that you get things in the right order. So it's always the top, it's the derivative of the top times the bottom, low d high. Guess it's in the backward order there, but whatever, as long as it's in some order, minus high d low, f times g prime, all over g of x squared. So as long as it's, that's a little less forgiving, you could switch the f and the g prime, or these two. Those you could switch, but you can't switch the two things on the top because it's a minus that it doesn't commute. The minuses are not commutative. All right, any questions? We're good? So this will be, I'll have this back for you tomorrow along with, whatever quiz, just so you know, when we do tomorrow's quiz, we grade it in class and you keep it because it's the one right before the exam. That's the way I usually do this. Let's move on. Today, we mainly just have to go over or remind you of a few things that you probably already know, and then take a look at the the practice test, just so you know where to find it and what to do for tomorrow. So those are my goals for today. And I guess there's some homework to look at as well. So we have f prime of x is the derivative. I think I have this in one of my PowerPoints, but I didn't want to have to dig it out, so I'm just going to write this down to remind you, and then we'll do a few examples. This is a rate of change. This is a slope. So just wanted to remind you that this derivative is literally a rate of change. It is a slope. So how much is one thing changing with respect to another? Classic example is when we talk about position. So you might have something like this. S of t, we use S of t to represent the position of an object in terms of time. So you might have something like this, negative 16t plus 50, t squared plus 50, is that right? Yeah, we'll do it that way. So you might have this, and this is the position. So this is the position of a ball thrown in the air. So something like this. So anytime you throw something up in the air, you get a function that looks something like this. And here the position is in, so the position S of t is feet in this case, and t is seconds. So if I have the position of this object, then the rate of change of the object is literally how fast this thing is moving. So as I throw it up in the air and it comes back down, how fast is it moving? And when we talk about how fast it's moving, velocity could be positive, moving upward, or negative, moving downward. So how fast this is moving is the derivative. It's the rate of change. So throw this thing up in the air and you get this thing. And so let's go ahead and figure out the velocity. The velocity of this object is the derivative of the position. And then once we have that velocity, we could talk about the velocity of the object after a certain number of seconds. So maybe 2 seconds after I throw it up in the air, we could figure out what the velocity is 3 seconds after I throw it up in the air. Ooh, that's no good. Sorry. I have to change these because this thing will hit the ground before 3 seconds. So I'm going to just change this to be 0.5, and will 2 work? No, 2 won't work. We'll use 1. There, that'll be more interesting. So I'll explain how I know that it's going to hit the ground before 3 seconds in a minute. But for now, let's go ahead and get the derivative of the position. You can do this. This is not hard. So derivative of position is velocity. Go ahead and compute that. And I'm finding my randomizer because I know everyone wants to be chosen, and this will make it blurred. I've got a guy in my statistics class who doesn't understand this concept that I'm randomizing the class, and he's always like doing this sort of thing. I'm like, come on, don't you understand? I want to get everyone involved here. I know you know the answer. He sits over here. So anyway, so Zach, what's the derivative of position?
Negative 32t plus 50.
All right, very nice. Plus 50. Okay, so now we can figure out, oh, whoops. I put that in the wrong place. Let me move it up here. There we go. That's where I need to put it. So there's position, derivative is velocity. Now that I have that, I can plug in each of these numbers to figure out how fast this thing is moving at each of these times. Oh, you know what? I could have done v of 2. Let's do v of 2 as well. V of 2. Could I have done v of 3? I could have done v of 3. I just realized v of 3. Yeah, this thing isn't going to hit the ground. Well, anyway, it doesn't matter at this point. Let's just do v of 0.5, v of 1, and v of 2. So first of all, Ethan, did you plug in 0.5?
I did.
What'd you get? 32, wait, 32 feet per second? Is that right?
0.5, 34.
34, okay. Yeah, I was going to say it's close, but not quite what I got. Okay, 34 feet per second. Nice units, by the way. So this is a velocity, it's feet per second. So half a second after I launch this thing, and I'm actually launching this much faster than this. So you have to imagine me being outside and giving it a good heft so that it goes up pretty quickly to begin. Anyway, this thing, after half of a second, it is moving upward 34 feet per second. So 34 feet per second, let me think, what's the conversion? 3,600 over 5,280. So what's that? Roughly 3/5, let's say. So 3/5 times this would be the miles per hour. So is that 25 miles per hour maybe? So it's moving pretty quickly, or 22 maybe, 22 miles per hour. Okay, anyway, that's really irrelevant. Bryce, what is the velocity after 1 second? All right, so it's slowing down, as you would expect. As this thing moves up in the air, you can actually see this thing slowing down as I throw it up. As long as I don't throw it up too fast, it's moving relatively quickly when I let go of it, and then it slows down as it goes up. Very nice. Next one, we're over to Allison. What about v of 2? -14. -14. I guess that means it's moving downward now. So this is after it reaches its peak and it starts moving downward. We're going -14 feet per second. So you go up and then you come back down. Very nice. So velocity is the derivative of position. It's a rate of change. This is all that's on your homework today, by the way, is we're just going to go over several examples of these 3 ideas: derivative, rate of change, slope. That's it. I know it seems like it's so simple. Well, let's go ahead and do the next level. So I don't know if you know what acceleration is. So let me try to explain. Acceleration is how quickly your speed is changing. So think of it this way: you're in your car and you mash the accelerator, which is the gas pedal. Oh, if you have an electric car, do you still call it a gas pedal? I don't know. It's interesting. I'll have to ask. I have 2 kids. 2 of my 3 kids have Teslas. I don't know. I guess that they have achieved more than I have in my life. All I've got is a Prius. But anyway, so I'll have to ask them what they call that, if they call it the gas pedal. But anyway, when you press the gas pedal, you accelerate. You get going faster and faster. And the way we measure acceleration is how much does your so change in velocity over change in time. Anytime you're doing a rate of change, it doesn't matter what kind of rate of change it is, any rate of change will be a derivative. And so we're trying to figure out how much does velocity change with respect to time. And so one way you could think of this is like delta v over delta t, which I guess that's kind of a bad way of writing that. Maybe dv over dt, which is v prime of t. So the important thing, though, for you is that the acceleration is the derivative of the velocity. So as I throw my stapler up into the air, using like outside, though, because I can't throw it as hard here. Anyway, I've got the acceleration will be the derivative of velocity. So let's go back up there and see if we can compute the acceleration. So acceleration is the derivative of the velocity. Excuse me. All right, who's next? Kelsey, what is the derivative of the velocity?
It would be -32.
Just -32. Yeah, that's right. So -32. Now, I don't know if you're a physicist, but some of you recognize that number, don't you? negative 32 feet per second squared. That's the acceleration due to gravity in imperial units. So that's the acceleration. And if you think about it, if this thing is free falling, and even if it's moving upward like that, it's free falling. It's the only force acting on this stapler after I release it is the force of gravity or the acceleration due to gravity. So that whole time, the only acceleration is the acceleration downward due to gravity. But the important thing for you to remember are these two equations. First of all, velocity is the derivative of position, and acceleration is the derivative of velocity. So rate of change, derivative. I have two more rates of change to do, and then we'll be done. Well, we won't quite be done because we need to talk about what you're going to do tomorrow with this test business. But those two rates of change. So let's talk about the let's see. So those are two rates of change. So let's talk about a population. Population P of t is equal to a population, the size of a population. Size of a population at time t. So in terms of like just words, what would you suspect P prime of t? What does that mean? Remember what P prime of t is and what derivatives are, but can anyone express, I want to pick, I'll let you, if like this kid that wants to always raise his hand, if you want to be that person, now's your chance. What do you think P prime would be? What do you think, Sienna? Yeah, so it's like how fast that population is growing during whatever time period we're talking about. If it's a year, or if we're talking about bacteria, it might be just a day or an hour even, but it's the rate at which the population grows. So this is the rate of population growth. Now, population growth is complicated. It's a complicated thing. And so the way that we're going to deal with it here is so simplified that if you are at all familiar with biology or growing bacteria, you're going to say, that's not right. It's okay. You all learned, well, maybe not all of you, you learned the Bohr model of the atom. That was a lie too. Okay, some of you know what the Bohr model of the atom is, but whatever. For now, we're just going to go with this, okay? Although it's not entirely a lie, what I'm going to show you. It's just not always true. In fact, it's very rarely true. So, in terms of the homework that you have, you're going to have what's called linear growth. So, linear growth. So what linear growth means is that every year, every day, every moment, whatever the time period is, you always get the same number of individuals. This is fiction, though. I mean, in real life, well, it's not entirely fiction. You could think of things that grew linearly, but imagine this: you have 10 rabbits this year. Next year, you have 12 rabbits. The year after that, 14 rabbits. You see how the growth is always 2 rabbits per year? 16 rabbits, then 18 rabbits, then 20 rabbits is next. Anyway, that's what linear growth is. Linear growth means this, that P prime of t is a constant. So you have some constant for the derivative. So the way that the problems in your book or in your homework are going to look are something like this. So here, we'll go back here. But linear growth, this is see new individuals per time period. So it's very similar to what Sienna said about this thing, is how many new things do you have per unit year or whatever it is, period. Okay, so here's the sort of thing that you're going to see in your book, or in your the lumen here, is it will say something like this, that you have some sort of a bacteria, and you know, they use bacteria, and bacteria never grows linearly. It's always exponential. But we'll set that aside for now and just think of this as being, well, we're just going to do this to learn about growth. And if we had exponential growth, it's going to be a different formula. It's more complicated. This is the baby step that we learned. It's like the Bohr model of the atom, which is just nucleus, and you have these various electron shells that are just going in circles. Anyway, getting back to this, so here's the sort of thing that we're going to see, is that you have, they'll say something like this, P of 0 is equal to 100 bacteria, and P of 4 is 800. Let's just say, I'm just making things up now. So let's say that this, and there is linear growth. So let's assume linear growth with this, and then they'll ask, well, what is P of 5? Okay, so here's how we're going to do this. I know it's like just a bunch of numbers, and we're trying to figure this out. So don't go with your intuition. I made the mistake of doing this when I first saw these problems in your book. I was just like, oh, I can just do this in my head. You know, we got this going on, and it's easy. And it turned out it wasn't quite so easy. So here's how you should do this: is actually start with this. P prime of t is c. Oh, I guess I should do this. Sorry. If P prime of t is equal to c, then P of t is c times t. Yeah, this is becoming more complicated than I thought. Okay, so c of t plus the original amount. Sorry about that. So that's what linear growth means. Sorry. So linear growth, I should have started with this perhaps, because we know how to do derivatives. But rate of change, if you do the derivative of this piece of 0 is the original population. So do the derivative of this, you get this straight line linear growth model. So anyway, we're going to work with this. And as you might guess, we're going to plug in these two things. First of all, this one, that actually goes right there. So P of t is c times t plus 100. And then you're going to use this stuff, that is t, this is p, to figure out what c is. So c times 4 plus 100. So 4c must equal 700, which means c is equal to 700 over 4, whatever that is. What is that? That's going to be 175. Is that right? So c is 175. And now we can figure out what P of 5 is. P of 5 is going to be 175 times 5 plus 100. So that's going to be 175 times 5 plus 100. I'm sorry, I know. It's embarrassing. I'm actually using my calculator. 975. I should have been able to do that one in my head. Okay, let me do one for you to do. So now you see how it works. You're always using this. So linear growth just means that there. I will rewrite that down here. P of t is equal to c times t plus the original. Okay, so what if I told you this? That P of 3 is equal to 800, and P of 3 is 4 times the original population. So let's say that this particular population quadrupled in 3 years, or whatever the time unit is. So it's quadrupled in 3 years, and we know that P of 3 is 800. So you need to know two things to do this. First of all, what is P of 0? And then after you do that, see if you can figure out what C is. That'll require a little bit more arithmetic. I think you can figure out P of 0 just in your head even. So take a minute, see if you can solve that one. And then we have one more type of problem to look at before we talk about the test. All right, let's get the P of 0. That one's the easy one. Caitlin, do you know what P of 0 is for this one?
No.
So P of 3 is 4 times P of 0. Here's P of 3. That's 4 times P of 0. So what's P of 0?
You just divide by 4.
Yep.
200.
Yep. Yeah, it was too easy. You wanted to do calculus. Don't worry, you'll get to do calculus, but not right this instant. All right, very good. Okay, next, I want to know what C is, but to do that, you're going to have to use this equation. So let's see if we can walk through this. Allie, what do we do to, like, what am I going to plug into this equation to figure out what C is? All right, so let's just, in case someone isn't quite tracking this, notice that what Allie did was she took this, P of 3 is equal to 800, put the 800 there for P of t, and the 3 is the t, so that went in for t, and of course we already know that P of 0 is 200. Very good. All right, one more, and then we're almost at home here with this one. So Sienna, what is C for this problem? Almost, yeah, you got the right idea. Yeah, here, let me just rewrite this and then you'll get it right. You're actually so close.
Oh yeah, wait. 200.
200, yeah. So the 20, I guess I think of that as being close to 200 in the sense that it's 1/10 of 200, but good job. Nice work. So now if you were asked to do something like this, what is P of 10? You could do that easily because we now have all the nuggets, all the pieces, all the chunks that we need for this. It's 200 times 10 plus the original 200, and that's going to be 2200. So, like I said, this is unrealistic. In reality, if you, like I said, the ones on the homework are things about bacteria. It's not realistic to think of those as being linear growth, but just go with it, run with it. Here's what it means to be growth, linear growth. Okay, one more thing, and then we'll talk about the test. And this has to do with revenue functions. Actually, profit functions, revenue functions, cost functions all work the same way. But let's go with the revenue function for now. So R of Q is the revenue generated from Q, whatever it is that we're selling, Q units, we'll say. So let's say that we are selling, we're selling bicycles, and if I have 1,000 bicycles that I sell, the revenue that I generate is from those, R of 1,000. So you might say, well, wouldn't it just be 1,000 times however much you sell it for? Well, not entirely true, because if you flood the market with bicycles, then the price that people are willing to pay for those bicycles goes down. And if you make the bicycles scarce, then perhaps the price would go up. Anyway, that's the idea here with these revenue functions. Usually revenue functions for whatever, not for whatever reason. I know the reason, but I'm not going to tell it to you because it's a secret. Actually, it's not a secret. It's just I want to blow ahead. And the revenue function usually is going to be quadratic. Something like this, you would have maybe 100q minus q squared, something like that. And so so you could compute something like the revenue generated from producing and selling 30 bicycles. In fact, we will do this. We could do the revenue generated from 40 bicycles. And once again, the reason why this is not a nice linear function is because we're assuming that market forces are going to dictate that if we produce too many bicycles, the price or the value will go down because there are too many. Like the Stanley Cups, for example, they were hard to get apparently for a while, and so the price, it's ridiculously high for a Stanley Cup, if you know what I mean, those mugs that apparently can withstand 1,000 degrees and still have ice in them. Okay, so let's go ahead and do R of 30. R of 30 is 100 times 30 minus 30 squared. So that's going to be 3,000 minus 900, which is 2,100. Ooh, 5 minutes to go. That was so loud. But anyway, so there's that. That just means that the revenue that I would generate, maybe this isn't a good realistic function here, but revenue generated from producing and selling 30 bicycles would be $2,100, probably more than that. But anyway, if we did R of 40 squared, so 4,000 minus 1,600 is 2,400. So we don't get as much bang for the buck, if you will, from producing those extra 10 bicycles, because notice that the revenue we get is just another $300. So the thing that we're going to be interested in is called marginal revenue. And this is literally defined as the extra revenue from producing one more, whatever it is, unit, item, whatever it is that we're making. So it's the extra revenue from producing one more unit. So this is the change in revenue. This is literally change in revenue over the change in number of items. Q there, by the way, is the number of things that you're making to sell. So marginal revenue, this is something from the business people, I guess, care about, is change in R over change in Q, the change in revenue per unit item. So for this one, R prime, it's the rate at which revenue changes with respect to the number of items we make. So this is easy enough, 100 minus 2Q. So notice that the rate at which revenue changes, if Q is really small, then the revenue goes up a lot for every additional item that you make. But then if you flood the market, maybe you have to put some of those items on clearance at the end of the season or whatever, and you start actually losing money. So if Q is more than 50, for example, then you end up having a marginal revenue that's negative, and if you produce more, you actually end up losing money because of whatever reason they don't sell. You end up having to put them on clearance, and they sell for too little. Okay, so I know we didn't really go over a good example of this, but the marginal revenue function's just the derivative of the revenue function, so it's pretty straightforward. Let me take a peek at the homework. The homework looks good. I think you'll be okay. there's something slopes. Well, slope, remember slope is derivative. Okay, so in addition to that, you will see up here the test one practice problems. I have not yet written up my answers to these, but you can still look at those. So that's what they look like. Eventually, hopefully tonight, we'll have to see how things go today because I've got all sorts of people who want to visit me today. But anyway, we'll see if I can get these written up. And once I get them written up, I'll put the answers. They may not appear until tomorrow afternoon, but for sure the answers will appear before Thursday. So hopefully today or maybe tomorrow, I'll get all of my answers, but we will discuss this tomorrow as well as having a quiz, homework, and so on. So be sure you look at this before tomorrow because it's a good example of what the test will look like. All right, I'm stopping the recording in case you want to chat. Otherwise, have a great day, and we'll see you tomorrow. Thanks for coming, by the way. Everyone was here. So exciting. Oh, I should do attendance since everyone was here. Great. All right. Well, let's do this next. I don't know. Couldn't tell you why it's there. It's just there. And there's one up here too. Wonder why. Hi, Josh. Can you see me? Okay, so far away. Whew. Nolan, are you going to be okay? It looks like you're about to perish.
We practice.
Yeah, practice. What kind of practice? Oh, fascinating. You're a coach.
Nope.
And how late were you at practice?
7:30 to 9.
Oh, that's so late.
It was in Centerburg.
In Cinnaburg. Fantastic. Oh, thank you. Wait. Joshua. What's that?
I'll be at the back.
Yeah. Rachel. Rachel, right? No, Morgan. Rachel? You're Rachel. Here's Claire. Did I skip you? Yeah. Okay. There you go. Senor, is that what it says? What do you got? Interesting. So I may have to fix that because I wasn't sure what would happen if I put it if I put the loop there twice. So you're saying it shows it's all done, but on the grade thing, it shows interesting. Okay. It's up to investigate. So you're not alone if that's the case. I just, I didn't know how that would. I was curious. I didn't know how that would. Yes, that's the great one. Now I should do that. So I'll have to go in and fix that. Yeah, for everyone, I'm sure you're not. I skipped you over here. Tyler. Is that right? Yeah. So, Ethan, keep getting better and better. And the right thing, now you've got robotic, right? You didn't hit that. Yeah. Maybe it's not working. Jackson, here you go. Cooper, welcome. There you go. Eli. Zechariah. There you go. Oh, Madison. Start.
Well, it was just, it was, you know, take the weight of the pollution and set it down at constant.